Almost live. Because we have people that follow us on YouTube and people that follow us with Zoom. Okay, seems works. Good. So we are in. So I want just to say everybody good morning, good afternoon, I don't know. I think maybe we are in Europe, more or less. Welcome back to this virtual series on complexity. We started in 2020 and this is the second appointment in 2021. On the web, just a few notes on the web page of the series, you can find the announcement of the next two seminars. This time we will have two seminars in March. One, there will be 12th of March with Giovanni Petri, Easy Foundation, and the other 26th of March with Luca Parmigiani of the Institute of Oncology Research of Bellinzona. Each seminar is about 40-45 minutes, and of course there is a discussion at the end. So please, you can free to take your or maybe write your answer, your question in the chat, or directly ask to the speaker. And we are recording the seminars, and the speaker acknowledge. I hope, yes, we ask you to record it, and they will be available on our YouTube channel. I think I said everything about, the boring stuff. So the speaker today, I'm very happy that he joined these virtual seminars, is Bernat Corominas-Murtra. So he got a bachelor in physics and linguistics and a master in mathematics. And he got a PhD at Barcelona in Spain. Then he moved to Vienna, and he was postdoc at the Medical University of Vienna in the section of complex system from 2016 and 2018. Then he's also associated researcher at the Vienna Complexity Science Hub. Then he moved as a postdoc at the Institute of Science and Technology in Austria, and he works mostly in theoretical biology and biophysics. He published a lot of papers on many things, in particular on biophysics, network theory, and informational theory. And from February 2021, so just now, he's assistant professor of complexity and the Institute of Biology of the University of Graz in Austria. So the floor is yours. Thank you to be here, and please.
Thank you very much. Thank you, Caterina, and thank you, Stefano, for these beautiful seminars and for giving me the opportunity of sharing my research with you all. As you see, I relaxed the title. So I said how randomness and collective dynamics define a stem cell, but then one thing I learned from biology is that categorical claims are extremely dangerous. So I decided to somehow start with an apology and say it may define a stem cell. So, we are going to talk about a basic building block of biological complexity, that this is the tissue. So tissue organization, I think there is no reason, there is no one here that is not convinced that tissues play a crucial role in organizing biological complexity. One of the most astonishing things of tissues is that, as Heraclitus would say with the river, they are never the same. They're in permanent renewal dynamics, meaning that cells are born in the tissues, are specialized, and then die. And this is happening continuously in a let's say flowing process, in a highly unbalanced process. And the key elements, let's say the governing elements of this renewal process, are what we call stem cells. Now we focus with adult stem cells. I will talk a little bit about non-adult stem cells in the embryo, but in development. But let's focus with what is an adult stem cell. Very briefly, from the end of the 19th century, it was somehow suggested that this tissue renewal, especially in what refers to the blood, must obey, or must be the outcome of a hierarchical structure that has some special type of cells that maybe functionally are not developing something that keeps the functionality of the tissue, but are responsible for this renewal. Then 70 years afterwards, approximately, it was observed for the first time that yes, indeed, at least in the hematopoietic, so in blood, so one could find, let's say, a tiny set of cells whose specialization was create offspring in order to renew the tissue. And this led us to the, let's say, standard or accepted definition of stem cell that is very tied to this historical development that put the hematopoietic stem cells in the center. So a stem cell is thought to be a self-renewing cell positioned at the top of a hierarchy that gives rise to a range of fully differentiated specialized cell types at the end of hierarchy's branches. And I would add, in order to keep tissue's functionality and homeostasis. These cells are supposed to be long-lived and are supposed to be clearly identifiable. This is, for example, in terms of the tissue of the blood, this has been a story of tremendous success, up to the point that many treatments nowadays, since years, are based on this scheme, on this organization of the tissue. So this worked fantastically well for blood, but for other tissues, it's not that obvious that this works so well. For example, long-lived, there is strong evidence that a lot of stem cells, so stem cells that can be identified as such due to some gene expression, biomarker distribution, and so on, compete neutrally in a way that only a tiny fraction of those who are stem cells actually act as stem cells. But the situation is even worse in some organs, like, for example, in the development of a mammary gland, where it's not clear what type of cell is the stem cell. To identify a stem cell in the mammary gland development, for example, one needs to track all the cells and record those who have been able to create lineages that were able to colonize the whole tissue. But there is not nowadays a clear biomarker that is telling us these are the stem cells in some organs. So then we need, let's say, if we accept, and I think this is an assumption that must be done, at least at the level of this study, if we accept the fact that the organization of the tissue is based, or the homeostasis of the tissue has as a building block the stem cells, then we need another definition. And then there are some proposals recently that are surprisingly simple, but at the same time surprisingly powerful. And one is a cell that has the ability to replace lost cells through mitosis. No reference to hierarchy, no reference to biomarkers, and so on. Simply the cell that is able to create a lineage that colonizes the whole tissue and keeps its functionality. So then, when we are removing the hierarchy from the system as something that it's imposed, when we are not talking about biomarkers, about gene expression, can we say that in part, or at least partially, stemness is an extrinsic, maybe an emergent property that depends on many context parameters, maybe geometry, maybe stochastic dynamics, maybe the location of the cell within the organ? This is a question that is complementary to the biochemical, let's say, approach. It's not a question that discusses. It's a question that says, well, what if this layer of complexity must be taken into account if the stem cell concept seems to be so evasive? And what we did with an excellent team of people is to, let's say, stress this hypothesis to the limit and say, well, let's assume that this is the fact and that there is no, what happens if there is no biomarker that is telling us this is a stem cell, this is not, there is no specialization, there are only cells that are proliferating and geometry and dynamics. It is not negating all the biochemistry. It's simply an approach that says, how much can we understand if we go towards the dynamical geometrical direction? So to be a little more specific, we took as a paradigmatic example the intestinal epithelium. For those who are not familiar with that, the intestines are these tubes. This is a common knowledge. And in these tubes, we have these undulations that are the villi. And when we see that these undulations are full of small invaginations, that this is what we have in the right panel. And these invaginations are what are called crypts. And at the bottom of the crypts, these are very microscopic, let's say, holes. at the bottom of these invaginations, we have what are supposed to be what have been reported to be the stem cells of the intestinal epithelium. The intestinal epithelium is a very important, let's say, tissue, because from this group of stem cells that lie at the bottom of these crypts, one has all these specialized cells that are crucial for nutrient absorption, for hormone secretion, and for many other functionalities that are crucial for life. So it's been identified that at this bottom of the crypt we have the stem cells, and what is being identified is that there is an overexpression of protein that is LGR5, and that seems to mark the stemness of the cells. So those cells having LGR5 overexpressed lie at the bottom of the crypts and act as stem cells. Very good. However, as I said before, it's been observed that most of these cells actually do not function as stem cells. Why? Because there is a neutral competition among them that was studied in this very beautiful paper 10 years ago, where they say, well, if we take a section of the bottom of the crypt and we start a neutral competition, this is equivalent of having a kind of random walk in one direction in this annular structure. Then what we see is that cells are proliferating, and some of them are competing, some of them are kicking out the neighbor, and so on. And in the end, we have only one lineage that survives out of these 10, 8, 12 cells that lie at the bottom, meaning that this neutral competition at this one dimension is actually removing an important fraction of potential stem cells from the system. That means that a fraction of these stem cells actually function as stem cells. But instead of taking let's say the horizontal section, let's take the vertical section. Then we have that the crypt can be divided in levels, and then let's assume that still this hypothesis that it was assumed before, that these cells lie at the bottom and all of them have more or less the same probability of becoming stem cells, and they are pushing the others up. How does it work? Well, this has been called the conveyor belt. Why? Because cells that lie at the bottom divide, and while dividing are pushing the other cells up. And this creates a net flow of cells that is like a conveyor belt. If this hypothesis is true, what we have at the dynamical level is that, okay, we have this let's say this green cell is the cell that lies at the bottom, then it divides. Here we have two cells, is pushing the gray cell up, and at some point it will colonize the whole tissue. Then there is a very important question here, is that, okay, what is the lineage survival probability in terms of the starting position of the lineage? So the green lineage started at position 0 or 1, and then at position 0, sorry, and then it was pushing up all the cells that were on top of it until it removed everywhere. So in this setting, the probability that the lineage will survive, will colonize the whole system, is 1 for the lineage whose mother cell was at the bottom, so at position 0, and 0 for the others. However, this is not what we observe. What we observe in reality is something close to that. A smooth decay. That means that some cells that did not start, the lineage did not start at the bottom, are able to go back to the bottom and then maybe recolonize the whole system. So how is this possible? Then if we take a look to the tissue and how is this renewed, we have said that this is like a conveyor belt. However, the situation is closer to that. There is this advection, there is this conveyor belt, but there is some degree of stochasticity. So from time to time, there is disorder. From time to time, there are relocations of cells. So in a word, there is noise in terms of the dynamical properties of the lineages. How this is implemented dynamically? Well, so we do the same we did before. So we focus in one cell that starts at a certain level, maybe here level, I don't know, 7. And then this cell can let's say, can suffer a couple of processes. The first one is to divide and push the neighbor up. But the other thing it can happen is that it swaps position with its immediate neighbor, meaning that it goes up 1 without being passed by advection, or it maybe goes down 1, let's say, flowing against advection. So that means that by chance, it could happen that this cell goes back and back and back and back due to these stochastical rearrangements, colonizes the first position, and then through division is able to colonize the whole system. We assume that this relocation, stochastic rearrangements, happen at rate Kr, and we assume that cells divide at rate Kd. This is a fantastic problem if we want to solve it using discrete mathematics. But one thing we can do is to use a continuous approach and create a kind of non-physical object that will be of use to make predictions. This non-physical object is what we call the density of lineage n at position x at time t. What is this density? This density is, let's say, how many cells would be in a given position if we are sensing the other cells through the advection, but we are not competing yet for the position. This is a mathematical trick that enables us to treat the system as a reaction diffusion system. So first of all, we have the advection term, okay, due to duplication of cells that lie below me. Then we have the reaction term. So we are proliferating, we are creating new cells. And finally, we have the diffusion term. So these stochastic rearrangements are creating a diffusion process. So all in all, what we have is a kind of a scary reaction diffusion equation whose solution has a wave. But the important thing is that this wave, even it never stops. Of course, in real systems, it stops because you find the final of the crypt. And let's say, there is no need to assume that it stops. But the important thing is that the value converges for each position to a certain, let's say, to a certain value, and then it becomes a flat distribution. Why is this important? Because then one can prove that the probability that this lineage is in a given position is proportional to this density. But more importantly, one can say that the amplitude of the fluctuations that are defined by this probability is actually defining the number of stem cells. What does it mean? That means that if one solves this system, that funny enough can be solved analytically quite easily. Well, quite easily. I mean, it's not. It can be done. Let's put it like that. Then you find that the probability that a lineage survives decays as a Gaussian, whose variance is actually Kr over Kd square root. That means that the fluctuations in this system have this scale, meaning that from 0 to sigma plus 1, because we consider this the first cell, this is the region where fluctuations make sense, where one can expect to see the system. Beyond this, we don't expect that a cell that started at position 10 can colonize the whole system. Although it could happen probabilistically, it's beyond the fluctuation scale of the system. So the fluctuations are telling us what is, the scale of the fluctuations are telling us what is the size of the stem cell region. This is the assumption. However, things are a little bit more dangerous because now we described something that is happening in one dimension, and we actually have something much more interesting than one dimension, because a real geometry of the crypt is something like an hemisphere coupled to a cylinder. So then this is a two-dimensional manifold. We have to redefine the rules in a reasonable way and according to what has been observed experimentally. And while doing so, one gets a very general system of equations where you have general geometries. But the important thing is that in the end, you have a prediction of the number of stem cells that is based on the geometry. This is the metric tensor of our manifold general geometry, and this is the strength of the fluctuations. So the number of stem cells depends on the geometry and the stochasticity of the dynamics. Funny enough, again, if we have hemispherical surfaces like the ones we have in the crypt, then it can be analytically solved using a couple of mild assumptions, and we have these kind of beautiful predictions that are ready to go to the real world and see what happens. If we go to the real world, first taking data that was already published some years ago from Risma et al., what we find is that, first of all, the decay that was observed experimentally in the probability of lineage survival more or less fits inside the interval of confidence a Gaussian with the given relation of the relocation rate and duplication rate, that in that case is around 1, that satisfies this Gaussian shape with this general solution. And we have that with this, we expect to observe 11 stem cells in each crypt. So, okay, so sorry, here I have to say, so this is actually what was reported in this paper, that around 11 stem cells, LGR5 positive cells, it is the number of cells that are observed in every crypt. So in that sense, the geometrical dynamical approach was fitting the biochemical approach. So in each crypt, we have more or less 11 stem cells in these experiments that overexpress LGR5, and we have 11 stem cells if we consider the dynamics and the stochasticity of dynamics and the geometry of the system. But we wanted to go further, and for that, I had, again, the opportunity to work with an excellent group of people, working experimentalists, working with the last technologists and the very best skills. And what we did is, okay, let's go to real organs. And they had a very interesting experiment where they were following the dynamics of the lung and the small intestines in vivo, using lineage tracing techniques and image in vivo imaging. And they had the idea that things were somehow not the same. The dynamics was not clearly the same. And then we say, well, let's see since you have this beautiful data, let's track what we see in time. What is the lineage survival probabilities? And let's see if we see dynamical differences in that. This is a transient, meaning that probabilities may sum up more than 1, because many lineages can let's say, be in the same crypt at the same time. And the probabilities may be in long term lower than 1, because we may not track all the stem cells of the system. So some systems simply result in no colonization, because the cell that colonized the whole system was not tracked. This is a technical detail, but what is clear in these plots is, first of all, we could fit with our theory the transient, which is very beautiful, not only the long term, but also the transient. But the second thing is that indeed, in the long intestine, things seem to fall faster than in the small intestine. So then the question is, well, how many stem cells in terms of LGR5 expression we have in each intestine? And funny enough, what is found is that we have more or less the same number of LGR5 plus cells. So the same number of cells overexpressing LGR5. So according to the stem cell marker, the large and the small intestines have the same amount of stem cells. They are more or less the same. They have more or less the same geometry, the same size, and they have the same amount of LGR5 cells. Nevertheless, we have seen the dynamics is strongly different. If we take the dynamics seriously, then we observe that there are huge differences. And essentially what we see is that the small intestine is 8 times more noisy than the large intestine. And both fit quite well with the Gaussian decay that is predicted by the theory. Then the question was, well, let's observe what's going on in the different levels and see if we are missing something. And our surprise was that if we take the small intestine in all levels of the crypt, we see that the probability that the clone remains there after 8 weeks is non-zero, meaning that the decay is smooth. But in the long intestine, only the cells located just at the very bottom or one position over the bottom were able to create remaining clones that could remain in time. The others were expelled. But look at this. We say that the LGR5 positive cells were the same in both, even more. In the large intestine, they are a little bit more. So then that means that the amount of stem cells having an active role in tissue renewal is completely different in both intestines, even the fact that even the observation that the stemness in terms of biochemical markers would be the same. So if we collect all these terms, what we find is that the prediction is that in dynamical terms, we will observe more or less twice as much stem cells in the small intestine than in the large intestine. And this is indeed what you observe functionally in the system. So in spite we have the same number of stem cells, the dynamics is much more noisy, as we see this curve, blue curve is much flatter than the red one, than in the small intestine than in the large intestine. We see that in the small intestine, all positions contribute eventually to some cell that eventually colonizes the whole system, while in the large intestine, only the cells located at the very bottom contribute to tissue renewal. This is a very shocking observation that is somehow saying that half of the supposedly stem cells of the large intestine have no functional role. They are not, it's not that they are competing neutrally and they are removed, is that they don't even have the opportunity of compete neutrally with other stem cells. So far, I've been talking about tissue renewal in the intestine dynamics. We reached this very interesting conclusion, shocking conclusion, I would say, or disturbing conclusion, that the biochemical markers do not fit with the dynamical geometrical markers. And now I want to go very briefly to development and to show some results we have regarding mammary gland development and kidney development. Again, I had the opportunity to work with a fantastic team, experimentalists and theorists from different institutions. So both kidney and mammary gland, while developing, are what are called branching organs, meaning that through development, what happens is that you have these tips, and these tips are growing due to luminal pressure and to the fact that new cells are appearing in the system, and at some point they branch, and they branch in a kind of a very interesting process. But the important thing for us is that in the tips of the branches is where stem cells are. So in the case of the mammary gland, these stem cells have been identified through lineage tracing techniques, because as I said before, it's not clear what biochemical marker is giving the property of stemness, or if even there is a biochemical marker with giving the property of stemness. So the important thing for us is that the stem cells lie at the tips, and this is from where the tissue grows. So the tissue goes from the tips and it branches and creating new tips until it stops for the reason that, okay, whatever reason, that it's not important now. So, but now, why is our framework kind of suitable for this kind of phenomenon? Well, it's a very funny thing that what we did so far works perfectly well if we perform a change of reference frame. So this is what we did when studying the intestine crits. We had this kind of cylinder coupled to an hemisphere, and then we kept the bottom of the cylinder, the hemisphere, let's say in rest, and then everything was happening, was moving up, and with respect to the bottom, and this is what we were observing. In kidney and mammary gland development, we have somehow the opposite. So we have that stem cells still lie at the bottom, or at the tip, and then they are proliferating and the tip is going in that direction. That means that we have exactly the same kind of dynamics. The only thing is that we are changing the reference frame. Now what is in rest is the cells that are being created, but the tip is what is moving up. So with that, we could prove that anything that we said before can be applied to this kind of organs. So anything that is true for a cylinder, for the dynamics of the internal manifold of the cylinder, is true for the dynamics of the external part of the cylinder growing up. This is a very beautiful property that enabled us to study this other type of organs. Actually, this formalism, as I shown before, depends. It can be applied to any geometry. Then the question is if it makes sense, the question is if you can solve it, but in principle, the formalization can be applied to any geometry where you have a privileged dimension where the system grows to. Okay, so one of the main ingredients of this theoretical framework is the existence of noise in terms of stochastic reallocations of cells. So the first thing is, do we have any evidence in the mammary gland development that we have stochastic reallocation of cells? And the answer is yes. If you see the cells that are circled here with this highlighted here, they start here together. And after some time, we see that they are separated, meaning that other cells occupy the position that they occupied before, meaning that there is noise in the system. So we have stochastic rearrangements in this system. Just a technical comment, the way we quantify that. So what we did is to study clone dispersion, and at some point we say, well, what is the minimum distance of all the clones that we are observing to the next neighboring cell? And then we created some computer simulations, and then at some point we could fit quite well, as you see, what was observed in real data with some parameterization in the computer simulation, and then the best fit was the one that was giving us, okay, this is the degree of dispersion in this system. So for the mammary gland, we found that the ratio between the stochastic intercalation rate and the duplication rate was, depending on the system, on the observation, between 2 and 5. Then, if we apply all the machinery, what we found is that, first of all, we could predict, but this is not yet tested because there are no data on that topic. We could predict what is the decay. We predict the Gaussian decay of the probabilities of lineages to colonize the whole system. And we could predict, of course, the number of stem cells according to the geometry and the noise that is given by this ratio. And taking the size and the geometry of the tips of the mammary gland, we could predict that the luminal stem cells, which are the ones that belong to the center, so this is a 3D structure, were about to be 170 plus this huge error, but this is due to the fact that we could not fit this. So the data was very noisy in that sense, or that there are very different levels of noise. And the basal cells that lie at the surface were around 37. Then using lineage tracing techniques, it has been observed that the luminal stem cell number is around 172, which is quite accurate. And the basal stem cell number is around 93, which is at most 3 times more than what we predicted. So here we failed. Well, I think it's healthy to show that things fail from time to time, but the interesting thing is that what happens with these basal cells is that they are geometrically very different from the others, meaning that the others are somehow symmetric. So you can infer that they are more or less deformed spheres, like cubes, if you want, but something that is very close to a sphere. Whereas basal stem cells or basal cells are very elongated. Actually, they are like 3 times more elongated than luminal cells, while they have the same volume. So this means that one should reshuffle a little bit or take into account this huge asymmetry in these building blocks in order to construct this theory more suitable to cells that are not that, let's say, beautifully symmetric. Well, this is a prediction, as I said, it's not tested. And I will finally go to the kidney development, where we have kind of the same abstract structure than the one we found in the mammary gland. And one thing that is important that for kidney development is that it was observed from early observations of lineage tracing techniques and experimental work that it was a really, really noisy system. So a very dynamic system. So then we used a different technique than the one we used both for the mammary gland to infer noise. And we found that an independent fit, so like what we did before, sets that the ratio between the stochastic rearrangement rate and duplication rate is 16. So this means that the tissue is really noisy. The tissue is kind of in a high temperature. And of course, the prediction of the Gaussian is this one that I am giving here. And if we try to fit real data with that, we see that, okay, data is noisy, but still almost all points lie in the confidence interval, meaning that this seems to be a good explanation for the profile that is observed. Finally, we can predict the number of stem cells using our, let's say, theory. and we set this being 90. But this is a prediction because it has not been tested to my knowledge so far. I will finally make an observation. So we have been working so far with all these predictions, let's say, so the probability of lineage survival, we see that our theory is able to fit the transient, we put general topology geometries there, and so on. Now the question is, let's explore a little bit the theoretical consequences of our predictions. If geometry and noise determine or are about to determine or may determine, or let's say play an active role in determining the stem cell region, then we have this very interesting puzzle. So if we have very curved geometries, very tiny, let's say, filaments, then the stem cell region will be very small. We will have a few number of stem cells, meaning that we will have low chance of mutation. But if a mutation appears there, it will be very difficult to remove. This is also true if we have very low levels of noise. If we have very low levels of noise, we will have a very small stem cell region, a very low chance of mutation because we will have only a few cells in the stem cell niche. But if there is a mutation, it will be very difficult to remove. But at the same time, we can go to the other scenario, let's say very flat geometries or very high levels of noise. And what we will have is a big stem cell region, meaning that mutation can appear quite easily in this stem cell region. But if there is a mutation, this flat geometry or this highly noisy dynamics can make this mutant cell easy to remove. So I think that what is very beautiful here is that if one could find a mechanism to tune the noise, so to tune the rate of stochastic rearrangements, one could use that to tune the size of the stem cell region up on demand. At some point for a given treatment, it can be interesting to have a super noisy environment that everybody is competing just to give the opportunities of some malignant cell that is in the wrong position to get out. But sometimes you want to keep the stem cell region very small because you know that this is what works. I'm not an expert in this kind of cancer and so on therapies, but I think that this is giving us a hint that maybe can be interesting. So now we go back to physics, and if we were physicists, I mean, we're physicists talking about stem cells, and we had to summarize what we did so far, is that, okay, we can claim that the stem cell number may emerge as a consequence of the dynamics and geometry. In statistical mechanics terms, what we have is a microscopical dynamical hypothesis that gives rise to macroscopic prediction. In particular, we have that the microscopical dynamical hypothesis is the stochastic conveyor belt over realistic geometries, and the microscopic prediction is the lineage survival statistics and the functional number of stem cells. And we have seen that this approach can have predictive power in kidney development and in mammary gland development. So this approach is not, let's say, organ or tissue specific. It can be applied to other organs. So then this opens, I think that the leading question with which I open this talk, I close this talk. So is there a dynamic definition of stem cell? This is a very big question. I'm sure very difficult to answer, but in between, we should try to answer what is the source of noise. So now we have these fantastic imaging techniques, and we see that these tissues are really noisy, are at high temperature, not kelvins, but in terms of internal agitation. Is the source of noise generic? Is tissue specific? Is it responding to some kind of frustrated cell migration? Or is it related to rigidity properties, stiffness properties of the tissue? And of course, this is important. So how do the properties of the tissue itself affect the generation of the stem cell region? So suddenly we have a very stiff tissue because we overcome some kind of parameterization, for example, in the cell shape or in the structure of the cytoskeleton. Then we may end up in a stiff tissue, and then all these movements are not possible. How does it affect the stem cell niche size? Or the other way around, how does the stem cell dynamics affect this stiffness? And then I think that I think it's of crucial relevance, maybe the most crucial point here is what is the relation of what I have said so far with biomarkers. So we know a lot. There is tremendous amount of successful research, meaning successful meaning that elucidating mechanisms and able to create predictions that is based on the biochemical nature of different cells and cellular environment. So how is it interacting with the geometry and the dynamics? What are the feedbacks? Because I'm sure that the feedbacks here are in both directions. Then a very general question. So if we accept this dynamical nature of the stemness, we could go further and then, well, all the specialization is something that is not only or not maybe hardwired genetically in the cells, but maybe is let's say the response to a kind of a ecological principle that organizes tissue or the organ. And finally, how can this helps us? How could this help us to understand disease? So we have seen that more dynamic tissues have larger stem cell regions, but we can also play with the geometry. So is it giving us any hint on in the understanding of disease? So as I said before, this is something that we have been working with a big team of people with whom I had the honor, pleasure, and joy to contribute. People from the Netherlands Cancer Institute, people from Leuven University, people from Cambridge, people from the IST, and myself now at the University of Graz. And thank you very much. So I will be very happy to answer your questions.
So thank you so much. It was very, very interesting. I open the discussion. Yes, very good. We can't, but thank you so much. I have questions, but I want to first people. Stefano probably has a question, probably the same of mine.
Yeah. Can I make a question? Have a question?
Yeah, we hear you very well.
Okay, sorry, because I don't see myself. I don't know, that's a problem. So I would like to first thank you for this talk. Very nice and interesting, and I enjoyed it very much. And so I want to connect with the last things you said about the mechanical aspects, because we had some time ago, we wrote a model of stem cell development in the crypt, in which we try to couple the dynamics of stem cells with the mechanical cues received by the fact that, of course, there is a finite space. So it's not only geometry, which in our case was very simplified, but so the shape was simplified, but also the mechanical forces and how the spindle orients in response to the mechanical forces to generate this. And so I would like to hear a bit your opinion. We can pass you the paper and we'll be happy to hear your opinion about it. And we would like to know what you think about this issue of how much mechanical control is responsible for the type of structure you see. And of course, we had some experimental data from the time, but maybe one can maybe expand this issue a bit further.
For sure, I will be very happy to see this paper. I forgot to say something, and I'm very grateful that you raised the mechanical forces, because I didn't say a word on mechanical forces, which is close to not correct. The reason is that we are assuming here in this model so far that the tissue has a kind of constant density. That means that there is something that is keeping the tissue in a let's say in a specific density, and we take it for granted. But of course, the fact that the tissue maintains and keeps certain density and plays with this density is crucial, and this is due to mechanical forces that result from cell-cell interaction. So yeah.
Yeah, yeah, that was our question. We started exactly on what you said now. So that was our question. And the postdoc turns out that lives in Vienna now. So I don't know, he's in Austria. It was really a nightmare, that work. No, we work very hard, and then we decided to forget about it.
Okay.
I have a question about, so no question, but a comment about the story of the biomarkers, because it's something that I always have in mind. So, I mean, it's not a big deal, the story of the market, because, you know, biological markets are not perfect at all. So we define some markers because we maybe connect with some function that we know for other things or something like that. And then we enrich the population. I work mainly on cancer cells, but in cancer is even worse because we don't know even if it's involved in some way in the phenotype, or it's just there for some reason. So I think that your prediction, I trust more your prediction. I mean, I'm not worried that, you know, the numbers is not exactly the name. Biology is a little bit not so precise. So I will trust more your prediction, maybe in the future, no, when the markers will be better. I mean, there is no perfect market anyway in biology, so it's hard to answer this question in my field. Yeah, and I completely agree with everything because I work exactly on cancer cells and noise to change the phenotype, you know, of the cells and the plasticity of the cells. And it turns out that when you find a way to change the noise, change completely the capability of the cells to, yeah.
No, for me, the reason, so I think that I totally agree with that. So this work I presented, especially the one, the first one, was provocatively neglecting the markers, let's say. But I think that at some point one should agree with what's going on biochemically and what's going on dynamically. And yeah, so, but it's true. So
yeah, but unfortunately, there are some limitations. In particular, I mean, mammary, you know very well. It's okay. Probably intestine is better, so there are markers that works just by luck.
Yeah.
But in the mammary, perhaps there is also debate. And
no, it's not. As far as I know, so the experts I talked with, the Colleen Shelley, for example, she's an expert working with us on that, and she told me that. No, there is no conclusive.
Yeah, exactly. So I say no worry that the numbers not. I think it's matter of biology.
Okay.
So other questions, please.
I have a question. Maybe I missed something, or did you define the survival probability of a stem cell of the lineage at a fixed time or at a certain distance from the bottom? So the difference in survival probability is because of the geometry of the niche, or it's time dependent?
So I did both. So let's see if I go to, so here in this slide, so this is the general expression we have here. That is the relation between the probabilities that we have at 0 and the probabilities of, okay? This is a kind of rescale probability. In these probabilities, what we compute is what is the probability that the time t, the lineage Cn, so the lineage that started at position n, like 3, 4, whatever, is in the position, for example, now between 0 and L, so inside a given interval. So we have both. We have the probability that, so in general, this framework can predict the probability that a given lineage, meaning that a lineage whose mother cell started at a given position, is at a given position and at a given time.
And this position, the total number of positions you are considering is dependent on small and large intestine?
No.
Are they different?
No, they
so
are not.
The size, the distance is the same for both.
Yeah, the size is the same. Yep. There are no, let's say, as far as we know, we can consider them geometrically quite equivalent.
Okay.
Alberto?
Thank you.
Please.
Yes, thank you. Thank you very much for the very interesting talk. And I have a couple of short questions, I think. The first one is when you do I understand correctly when you say marker is, in your case at least, a single gene expressed, or you have a more a panoramic view of gene expression?
No, it's when I say marker, I say some biochemical property that could be attributed to a given cell and then having a phenotypic effect. But I'm not saying that I mean, in the case of the intestine, it seems to be very clear that LGR5 positive cells act as stem cells. So the offspring of these cells can give rise to all types of cells that populate the epithelium.
So it's just one gene.
In that case,
in that case, okay.
In that case, but in general, I'm just saying. So I'm just creating a complementary perspective from the fact that, let's say instead of marker 1 gene or 2 genes, let's say the biochemical ID of the cell. Then it can be one marker. So I know that in the mammary gland, they are playing with 6-7 markers to check if the combination of them may be the footprint of stemness. But I don't know how far they are. Yeah.
No, I'm asking these questions because I know of some work done on the stochasticity itself of gene expression.
Yeah.
Stemness. So that's why I was wondering. One can really define a marker for stemness. That's my point.
Yeah. This is in line to what Katarina said. No, it's maybe it's intrinsically noisy. It's not only the fact that we have problems in
right. That's my feeling.
Yeah.
And if I may, second short question: have you any knowledge of this kind of model done in plants, in meristematic tissues of plants, in plant growth, or just in animal tissues?
So I was talking. So a very interesting thing that happens in plants is that it seems that for example, in the roots, you have the stem cells at the tip of the roots.
Mm-hmm.
And one could think that, okay, these branching organs that I've been showing so far could be, let's say this structure could be similar to the one you find in roots.
Mm-hmm.
However, it seems that what you actually have in plants is something like that. Sorry. Because there is really a few relocations. So in plants, it seems that when a cell has a neighbor, this neighbor never changes.
Yeah, it's reasonable because of the cell wall properties. Yeah, okay. Yeah.
So then you are in this, let's say, trivial scenario where the cells at the very bottom are the only ones who are stem cells. And actually, it seems that there are experiments that they're following the lineage tracing in plants, and they see really strips that belong to each stem cell that it's colonizing this tiny fraction of the root with perfect, let's say, linearity. So in that sense, this model is not that interesting in plants.
You don't have that kind of noise. You might have other noise, but not this.
Exactly. So I maybe, but it seems, and I'm not an expert at all in plants.
No, yeah. I'm not an expert in stem cells in general. I'm just interested in noise and okay. No, sorry if I don't want to take time. Thank you very much.
Thank you for these questions. Very interesting. By the way, but the plants, I don't know anything about plants, but I was thinking the plants are also the cells are very plastic, no? That's the one if I know well, maybe I don't know very well. So I'm very plastic, so I'm thinking about.
Yes, it's true.
It's correct. It's true.
Yes.
No? Okay. I don't know anything. Just
no, but by definition, plants are plastic. Yeah.
Plastic.
The fact that even you can have an adult differentiated cell becoming meristematic, so it's yeah.
So that's I was thinking. Okay. Do we have other questions, comments?
Yes, can I ask just a question?
Sure, please.
Thank you so much. I'm not a biologist. So my question is only kind of curiosity. in your presentation, you give an equation about, in this equation, if I understood correctly, there are with this parameter about the geometry and about noise. And when you when you said noise, you said yes, in terms of stochastic rearrangement, or
Yes.
you say the stochastic relocation of
Yes.
cell position. And after that, in a question, we talk about the possibility to change the noise. My question is, I'm not a biologist, I've not studied this kind of stuff because I'm a philosopher. How can you intervene on noise? How can, because if we have this parameter in the equation that you give us, and there is this kind of noise, but actually it's possible to intervene on the parameter of noise.
This is a big question. The first thing one should understand is what is the source of noise.
Yeah.
Oh, and it's not clear at all. It's not clear if it's a generic source, because tissues are in this fluid-like state. So there is a lot of theory recently, beautiful theory on different states of tissues, and very interesting results are popping up, which are, by the way, very interesting because are showing facets of physics which are specific for biology. So really peculiar phase transitions, let's say second-order rigidity, things that are not common in, let's say, non-living materials or difficult to find. And all these works are about how is the tissue in terms of internal motion. So what are the conditions that make a tissue, for example, let's say fluid, in the sense that a cell can travel with no problems, and at some point the tissue can be totally stiff. So, and these are processes that are highly nonlinear, they are phase transitions, and it's, I mean, we know a lot about what is the let's say the mathematics, how this might work. We know, for example, that in the fact that you have interstitial fluid can trigger movements. We can think about frustrated migrations, but we don't know yet. As soon as we know what is the source of noise, one can act over that, and then hope that this action is not killing other, which is something that happens commonly in biology. So that you intervene in one phenotypic expression, but then you have a lot of consequences out of that.
Yeah.
Thank you so much.
I don't know if Stefano is here, because we published recently on Nature Reviews something of noise exactly. So we studied the unjamming and jamming, and publish comments and a discussion about this. Yes, I don't know if Stefano is here because he had another meeting, but if you look, because we work on this jamming and jamming, in migration is very important, and
yeah, for sure.
Yeah, maybe it could be useful. So very nice question. Okay, do we have other people that want to ask something? I don't see anyone.
Maybe one question from my side. Now you only incorporated dynamical behavior of the stem cells, but in this small intestines there are also like external signaling from different signaling pathways. Did you also think about how to incorporate them into your model?
How to answer this question? So the final goal would be that all the agents playing a role should be there, in a theoretical framework. What this framework I presented here, so what this framework is doing is to show that the geometrical and dynamical component somehow can give some responses. So I'm not passive. I'm not the landscape. As something that is playing an active role. Then what to do with all this signaling? So you have also this, for example, in the intestine, you have the Paneth cells, so you have a very complex architecture. For me, what is important is what question do we want to ask? What question do we want to answer? And then let's see what do we need. So your question would be interesting in the, for example, in the framework of is there any interference of the geometry plus for sure mechanical forces and dynamics in the, let's say, in the expression, inhibition, it's promoting some signaling, then that plays a role, for example, in the definition of stemness or in, I don't know, specialization, then I would incorporate this. But it would not be that I incorporate this in the model, but let's say that the model plays the geometrical dynamical role and helps to create a bigger picture of the problem. I wonder if I am answering your question. Essentially, what I want to say is that if the question incorporates this, then we will try to have a framework that combines both.
Yeah, I think you're totally right. I think it depends on the question you want to answer. Yeah.
So, other questions? I'm looking around. Okay. I think it was very interesting. The discussion was great. I really thank you so much to be part of this series, and keep in touch. We hope to see you in person once when it will be possible.
Yeah, that's far away, so.
Yeah, no, not so far. We are not so far, actually. We are in the same, country, in lockdown in the same countries, actually, more or less. Okay, so thank you so much. Thank you for all the people that joined this webinar. Next will be 12th of March, and Francesca will be the moderator, and we will have a discussion of a new nature physics appeared recently, 2 weeks ago, from the Foundation and Giovanni Petri. So I hope to see you again. Thank you so much, all of you, and good afternoon. Thank you.
Thank you very much. It's been a pleasure.
Thank you.
Thanks very much.
Thanks.
Bye-bye.
Thank you.
Bye.
Thank you so much. Bye-bye.
Last.